The solar system is composed of a set of radically different types of planets and moons. It has the gas giants Jupiter, Saturn, Uranus, Neptune to the rocky inner planets. Centuries of studying Earth and its neighboring planets and the meteorites have enabled the development of models of the birth of the solar system. Astronomical observations from increasingly powerful telescopes have added a new dimension to these models, as have studies of asteroids, comets, and other planets via spacecraft, as well as geochemical studies of stardust and meteorites. Earth is the third planet of the 9 planets orbiting the Sun in the solar system. The universe is composed of several galaxies. Our solar system is part of Milky Way galaxy, which is disc-shaped with about 400 billion stars of varying sizes. Our solar system consists of 9 planets and 31 satellites and a belt of asteroids. Origin of Earth. Theories about origin of Earth. Nebular hypothesis, Kant and Laplace, 1755. This hypothesis suggests that the solar system formed through the condensation of a nebula which once encircled the Sun. The outer planets formed first, followed by Mars, the Earth, Venus, and Mercury. This hypothesis suggests a sequential origin from outermost planet to innermost. As per this hypothesis, Mars evolved earlier than the Earth. This hypothesis is widely accepted to explain origin of different planets. During the past, the entire solar systems existed as a hot gaseous mass called nebula rotating in space. With time, the gaseous mass or nebula cooled and contracted. Due to contraction, there developed a bulge at the equatorial region. This bulge subsequently separated into several rings. The ring coalesces in the form of a globe and continues to revolve around the nebula. In a similar manner, 10 rings were formed, of which 9 of them gave rise to 9 planets. One broke down into smaller fragments to form the group of planetoids, while the remnant of the pre-existing nebula formed the central incandescent mass of the solar system and is known as the Sun. The planets were originally gaseous but were subsequently cooled down into liquid and ultimately to the solid state. Planetesimal hypothesis, Chamberlain and Moulton, 1905. This is the theory of biparental origin of the solar system. This theory postulates that due to the near approach of a larger star, tidal distortions were raised upon the surface of the Sun, and these, in conjunction with the eruptive force prevalent in the Sun, known as the solar prominence, brought about a description of the mass of Sun, and a number of gaseous bulbs were shot forth in space to great distances. These gaseous solar materials thus ejected in space were subjected to immediate chilling, resulting in the formation of a number of minute solid particles known as planetesimals. These planetesimals continued to rotate round the Sun in highly elliptical orbits. At points of intersection of the orbits, planetesimals collided, whereby the small planetesimals continued to coalesce, gradually giving rise to the planets. During the collision and coalescence of the planetesimals, large quantities of heat must have been generated and were dissipated in space before the next collision could occur, and accordingly the planets must have been solid all the time during the growth. This theory accepts that the collision must have taken place in quick succession and accumulation of heat might have caused a melting of the masses of the planets. Gaseous tidal hypothesis, Jeans and Jeffreys, 1925. This also accepts the idea of biparental origin like that of planetesimal hypothesis, but differs in describing that the Sun, that is, the solar prominence, had anything to do with the formation of the planets. According to Jeans and Jeffreys, during the ancient past, an extremely large star, while moving in the space, chanced to approach the Sun. Due to progressive and nearer approach of the star, a tidal pull was raised on the surface of the Sun, and this increased in with the nearer approach of the passing star. At the stage where the passing star began to recede, the tidal pull on the surface of the Sun thus formed was detached from the body of the Sun in the shape of a spindle bulging near the center and tapering at both ends. This very large mass of gas thus ejected in space was naturally extremely unstable and was immediately broken down into a number of small fragments. In all, 10 such pieces were formed, 9 giving rise to the planets and 1 which was broken down into pieces to the group of planetoid. These fragments formed into globular masses revolving round the Sun along definite orbits and cooled down gradually from the gaseous to the liquid and ultimately to the solid state. This hypothesis is the most popular one due to simplicity and capability of explaining the coplanar placement of the planets and the features relating to the distribution of mass and density in them and the density stratification that exists within the Earth. The Big Bang Theory. A Belgian priest named Georges Lemaitre first suggested the Big Bang Theory in the 1920s when he theorized that the universe began from a single primordial atom. The idea subsequently received major boosts by Edwin Hubble's observations that galaxies are speeding away from us in all directions and from the discovery of cosmic microwave radiation by Arno Penzias and Robert Wilson. Before the Big Bang, scientists believed the entire vastness of the observable universe, including all of its matter and radiation, was compressed into a hot, dense mass just a few millimeters across. This nearly incomprehensible state is theorized to have existed just a fraction of the first second of time. Big Bang proponents suggest that some 10 to 20 billion years ago, a massive blast allowed all the universe's known matter and energy, even space and time themselves, to spring from some ancient and unknown type of energy. The theory maintains that in the instant a trillionth of a second after the Big Bang, the universe expanded with incomprehensible speed from its pebble origin to astronomical scope. Expansion is apparently continued, but much more slowly over the ensuing billions of years. Description of distance and time. Light year. A light year is a measure of distance and not of time. Light travels at a speed of 3 lakh km per second. Considering this, the distances the light will travel in 1 year is taken to be 1 light year. This equals to 9.47 trillion kilometers. The mean distance between the Sun and the Earth is 14 crore 95 lakh 98,000 kilometers. In terms of light years, it is 8.311 minutes. eon. In geochronology, time is generally measured in Maya mega years or million years ago, each unit representing the period of approximately 1 crore years in the past. The history of Earth is divided into 4 great eons starting from 4540 MYA with the formation of the planet. Each eon saw the most significant changes in Earth's composition, climate, and life. Each eon is subsequently divided into eras, which in turn are divided into periods, which are further divided into epochs. Description of different eons. Hadean eon 4540 to 4000 MYA. The Earth is formed out of debris around the solar protoplanetary disk. There is no life. Temperatures are extremely hot with frequent volcanic activity and hellish environments. The atmosphere is nebular. Possible early oceans or bodies of liquid water. The Moon is formed around this time, probably due to a protoplanet's collision into Earth. Archean eon 4000 to 2500 MYA. Prokaryote life, the first form of life, emerges at the very beginning of this eon in a process known as abiogenesis. The continents of Ur, Valbara, and Kenorland may have been formed around this time. The atmosphere is composed of volcanic and greenhouse gases. Proterozoic eon 2500 to 541 MYA. Eukaryotes, a more complex form of life, emerge, including some form of multicellular organisms. Bacteria begin producing oxygen, shaping the third and current of Earth's atmosphere. Plants, later animals, and possibly earlier forms of fungi formed around this time. The early and late phases of this eon may have undergone snowball Earth periods in which all of the planet suffered below zero temperatures. The early continents of Colombia, Rhodesia, and Pannonia may have formed around this time in that order. Phanerozoic eon 541 MYA to the present. Complex life, including vertebrates, begin to dominate the Earth's ocean in a process known as the Cambrian explosion. Pangea forms and later dissolves into Laurasia and Gondwana. Gradually, life expands to land and all familiar forms of plants, animals, and fungi begin appearing, including annelids, insects, and reptiles. Several mass extinctions occur, among which birds, the descendants of dinosaurs, and more recently mammals emerge. The rise and evolution of the human species occurs at the very recent phases of this eon. Age of the Earth. So far, scientists have not found a way to determine the exact age of the Earth directly from the Earth rocks because Earth's oldest rocks have been recycled and destroyed. The ages of Earth and Moon rocks and of meteorites are measured by the decay of long-lived radioactive isotopes of elements that occur naturally in rocks and minerals and that decay with half-lives of 700 million to more than 100 billion years to stable isotopes of other elements. These dating techniques, which are firmly grounded in physics and are known collectively as radiometric dating, are used to measure the last time that the rock being dated was either melted or disturbed sufficiently to rehomogenize its radioactive elements. An interesting feature of these ancient rocks is that they are not from any sort of primordial crust, but are lava flows and sediments deposited in shallow water an indication that Earth history began well before these rocks were deposited. In Western Australia, single zircon crystals found in younger sedimentary rocks have radiometric ages of as much as 4.3 billion years, making these tiny crystals the oldest materials to be found on Earth so far. The source rocks for these zircon crystals have not yet been found. The ages measured for Earth's oldest rocks and the oldest crystals show that the Earth is at least 4.3 billion years in age, but do not reveal the exact age of Earth's formation. The best age for the Earth, 4.54 giga-annum or Ga, is based on old mineral grains, zircon, with uranium-lead dating method. The oldest dated moon rocks, however, have ages between 4.4 and 4.5 billion years and provide a minimum age for the formation of our nearest planetary neighbor. The age of 4.54 billion years found for the solar system and Earth is consistent with current calculations of 11 to 13 billion years for the age of the Milky Way galaxy based on the stage of evolution of the globular cluster stars, and the age of 10 to 15 billion years for the age of the universe. Inner structure of the Earth. The Earth was in a volatile state during its primordial stage. Gradually, density and the temperature inside increased. As a result, the material inside started getting separated depending on their densities. This allowed heavier materials like iron to sink towards the center of the Earth and the lighter ones to move towards the surface. With passage of time, it cooled further and solidified and condensed into a smaller particle. This later led to the development of the outer surface in the form of a crust. During the formation of the moon, due to the giant impact, the Earth was further heated up. It is through the process of differentiation that the Earth forming material got separated into different layers. Starting from the surface to the central parts, we have layers like the crust, mantle, outer core and inner core. From the crust to the core, the density of the material increases. Tectonic plates. Tectonic plates are layers of rock inside the Earth. The crust and the upper mantle form lithosphere. Under the lithosphere lies a fluid rock layer called asthenosphere. The rocks in tectonic plates are able to float upon the asthenosphere. There are 7 large and several small tectonic plates exist. The largest plates include the Pacific, North American, Eurasian, Antarctic and African plates. Continental drift theory. The huge land masses of the Earth are in constant movement. The continents and the oceans rest upon rock plates. They move relative to each other at rates of few centimeters a year. Until 200 million years ago, the continents were connected into single landmass called Pangaea. This Pangaea splits and pieces drifted apart, creating 2 new continents 160 million years ago. The landmass that was to become India separated and moved northward 140 million years ago and hit another landmass, leading to the eruption of the Himalayas. Australia separated from Antarctica 100 million years ago. The 2 supercontinents then pulled apart east and west, opening the Atlantic Oceans. The continents are still moving even today. The continental drift makes the Pacific Ocean smaller, the Atlantic Ocean larger, and the Himalayan mountains taller. The Atlantic Oceans become wider, Mediterranean Sea collapses and Australia reaches equator in 60 million years. Outer atmosphere and hydrosphere. The present composition of the Earth's atmosphere is chiefly contributed by nitrogen and oxygen. There are three stages in the evolution of the present atmosphere. The first stage is marked by the loss of primordial atmosphere. In the second stage, the hot interior of the Earth contributed to the evolution of the atmosphere. Finally, the composition of the atmosphere was modified by the living world through the process of photosynthesis. The early atmosphere with hydrogen and helium is supposed to have been stripped off as a result of the solar winds. During the cooling of the earth, gases and water vapor were released from the interior solid earth. This started the evolution of the present atmosphere. The early atmosphere largely contained water vapor, nitrogen, carbon dioxide, methane, ammonia, and very little of free oxygen. The process through which the gases were outpoured from the interior is called degassing. Continuous volcanic eruptions contributed water vapor and gases that the oceans are as old as 4,000 million years. Sometime around 3,800 million years ago, life began to evolve. However, around 2500 to 3000 MYA, the process of photosynthesis got evolved. Life was confined to the oceans for a long time. Oceans began to have the contribution of oxygen through the process of photosynthesis. Eventually, oceans were saturated with oxygen, and 2000 million years ago, oxygen began to flood the atmosphere. Composition of the Earth's crust. Chemical composition. Most abundant elements of Earth's crust in approximate percentage by weight is as follows: oxygen 46.6, silica 27.7, aluminium 8.1, iron 5.0, calcium 3.6, sodium 2.8, potassium 2.6, magnesium 1.5. Oxygen and silica are nonmetals constituting 74.3%, rest are metals. These together constitute about 98.6% of the total elements. The most abundant rock types in the crust. Rocks are divided into three broad groups: igneous, metamorphic, and sedimentary rocks. Igneous rocks. The oceanic crust is largely composed of basaltic igneous rocks which are covered by a thin veneer of sediments. The continental crust is much thicker and older. Virtually all the rock types known to man occur in the continental crust. Even meteorites and ophiolites constitute the continental crust. Important igneous rocks are granite, granodiorite, gabbro, basalt, diorite, and andesite. Metamorphic rocks. Common metamorphic rocks are slate, metamorphosed claystone, schist, metamorphosed claystone, higher grade than slate, quartzite, metamorphosed sandstone, marble, metamorphosed limestone, gneiss, metamorphosed igneous rock or sedimentary rocks, amphibolite, metamorphosed basaltic rocks. Sedimentary rocks. Roughly 3/4 of the continental crust is covered by sedimentary rocks and almost all of it is covered by loose sediments. Sediments consolidate to sedimentary rocks after burial. Sand turns to sandstone, limey mud to limestone, clay to claystone. Important sediments are sand, clay, and mud. Summary: Earth is the third planet in the solar system. There are four main theories about the origin of Earth, namely nebular hypothesis by Kant and Laplace, 1755, planetesimal hypothesis by Chamberlain and Moulton, 1905, gaseous tidal hypothesis by Jeans and Jeffreys, 1925, and lastly, the Big Bang theory by Georges Lemaitre, 1920. The history of Earth is divided into four great eons starting 4540 MYA with the formation of the planet, namely Hadean, Archean, Proterozoic and Phanerozoic eon. The age of the Earth is estimated to be 4.54 giga annum based on old mineral grains zircon with uranium lead dating method. Earth's inner composition is made of layers starting from the surface to the central parts. Layers are classified as crust, mantle, outer core and inner core. From the crust to the core, the density of the material increases. Tectonic plates or layers inside the earth. The crust and the upper mantle are the lithosphere. Under the lithosphere lies a fluid rock layer called asthenosphere. The rocks in tectonic plates are able to float upon the asthenosphere. Most abundant elements of Earth's crust are oxygen, silica, aluminum, iron, calcium, sodium, potassium and manganese. Thank you.